Hello, my people. Good morning, good afternoon, good evening. This is Dacian. I am happy to be here again. Welcome to Matify Analytics. In today's video, we are going to talk about some 10 top things that everybody must know about limits. I hope you are going to enjoy today's presentation, and if you happen to like the video, don't forget to click like the video and share the video to your friends. Is it your first time to be on this channel? Don't go without hitting that button. Hit the subscribe button and turn on the notification bell so that you get notified anytime we upload a new video. Okay, so without delaying, let's start. But before talking about these top 10 things that everybody must know about limits, let's first talk about limit itself. What is limit? What do you understand by limit? What do you understand by limit? When we look at this graph here, we can see this function f of x, and we have a point A and its image, and its value is L. So we say that L is the limit of our function f of x as x approach A. If as x gets closer and closer to A, f of x gets closer and closer to L. And how do we note it? And the notation is this one. We note limit of our function f of x as x approaches A equal to L. I repeat again, this point L is the limit of the function f of x as x approaches A if as x gets closer and closer to A, either from the left hand side or from the right hand side, then our function f of x will get closer and closer to that point L, and the notation is this one. All right. But the question is, when does this limit exist? When does this limit exist? This limit exists only if the value of f of x at the left hand side of A and the value of f of x at the right hand side of A are equal. And in this case, our limit A will be equal to f of x. Now, since we know when this limit exists and what the limit means, we are going to go deeper and see these 10 top things that we must know about limits. Must know number one, inspect the graph. When you have a graph, you can inspect it, and then from that graph, without doing anything, it's just looking at it, you can find the limit of a function at a given point. Let's see some examples. Example number one, look at this graph. At this graph, we have a point x equal to 3, and you can see that when you look at the graph of our function f of x, when x goes closer and closer to 3, either at the left hand side and at the right hand side, I'm showing it in green. So our function will be closer and closer to a value equal to 2. And this 2 is the image of 3. So the limit when x tends to 3 of our function f of x is equal to 2, because when x gets closer and closer to 3, either from the left hand side or from the right hand side, then our function gets closer and closer to f of 3, which is equal to 2. And let's see another example. Look at this graph now. On this graph, I have a function f of x in red. It is in red. And when we are at this point A, and you can see that at its left hand side, our function takes the value to be equal to 3.8. But at its right hand side, our function takes its value to be equal to 1.3. So what does this mean? This means that the left hand side limit of f of x at x equal to a is equal to 3.8, and the right hand side of limit of this function f of x at a equal at x equal to a is equal to 1.3. So you can see that these two limits are not equal. The left hand side limit and the right hand side limit are not equal. So this means that our function does not have limit at a point x equal to a. So this limit doesn't exist. So you see, when we inspect a graph, we can easily detect the limit of a function at a given point. Good. Must know number 2. How do we compute the limit when we have our function expressed as algebraic expression? Whether you call it algebraic expression or a formula or equation, whatever you call it. But when we have a function expressed as an expression, how do we calculate the limit? In this case, what we do when we have an algebraic expression, we make a direct substitution of our value a into our function f of x, and we come up with 3 different cases. The first case is when our function f of x is continuous at x equal to a. In this case, when it is continuous and if the value of the function of a is finite, it is equal to a given value which is finite, then the limit will be equal to f of a. And the other 2 cases is when the function is not continuous at x equal to a. The first case, we may get the value of f of x to be equal to a given number over 0. And in this case, the limit doesn't exist. We will get a vertical asymptote at x equal to a. And we will have to check the left hand side limit and the right hand side limit to see the behavior of our function at the left hand side of a and at the right hand side of a. And the other case is when we evaluate the value of our function at a and we get the value to be equal to 0 over 0. So in this case, we have an indeterminate form. So when we have an indeterminate form of this case, there is a number of tricks that can be used. When one of them is to factoring our expression, or use the conjugate of that expression, or you can use the trigonometric identity if you have a trigonometric expression, or you can use the hospital rule. Let's see this example. F of x is equal to x squared minus 4, and we are at x equal to 1. So in this case, if we are to calculate the limit when x tends to 1, of x squared minus 4. So this, because we have an algebraic expression, the first thing that we have to try is to substitute the direct substitution of x by 1. So this will be equal to 1 power 2 minus 4. So this will be equal to 1 minus 4, which is equal to minus 3. Yes, so and the other 2 cases, we are going to handle them separately. But this is the second must know. You must know that when you have an algebraic expression, the first thing that you have to try is the direct substitution. The third must know, infinite limits. If for instance, if we have f of a is equal to a given value, a given number, finite number over 0. So this gives us infinite limit. So we have that limit when x tend to a of our function f of x, this will be equal to infinite value. This is infinite. This is either plus or minus infinite. Well, it depends if we have a positive value here or a negative value. So this is a infinite limit, and this, when we get infinite limit, it doesn't mean that the limit exists. So the limit doesn't exist, but it is an indication of something very important. It indicates that at the point x equal to a, we have a vertical asymptote. We have a vertical asymptote, and this vertical asymptote has equation x equal to a. So this is the next thing that you have to know. Must know number 4. Indeterminate form 0 over 0. When you have indeterminate form 0 over 0, how do you deal with this? To deal with this, as I have told you, you sometimes need to rewrite your expression, and there is many different tricks that you can use to deal with this case. Either you can factorize your expression, or you can use trigonometric identities. If you are dealing with trigonometric expression, you can use the hospital rule, you can use the conjugate, yes, all those things. So let's, for instance, take an example where you can use a trick of factoring. The trick of factoring, let's take an example of this function. This limit when x tend to which value? 10 to 5 of this function, x squared minus 7x and plus 10, not 5, plus 10x over x minus 5. You can see that if you make a direct substitution, I'm sorry, it's not, this is plus 10, I mean plus 10, not plus 10x, plus 10, then over x minus 5. The first thing that you always have to do is the direct substitution. So if we substitute x by 5, you can see that we will get, this will be equal to 25, x squared, 5 squared, this is 25, minus 7 times 5, this is 35, and plus 10, and over 5 minus 5. So you see that this will be equal to 0 over 0. This is an indeterminate form that we have to deal with. And we can factorize our expression, and then we get the right limit. So how do we deal with this by using this method of factoring? It's just to factorize this x squared minus 7x plus 10. You can see that this is the same as x minus 5 and times what? Times x minus 2. Just two numbers whose product is 10 and whose sum is minus 7, it's minus 5 and minus 2. So then x minus 5 times x minus 2. Then our limit will be when x tend to 5 of x minus 5 and times x minus 2 and over x minus 5. And we simplify this. So this will give us limit when x tend to 5 of x minus 2. And this will be equal to 5 minus 2, which is equal to 3. So you see, that's it. Factoring. So let's take another example. Where we can use example number 2, where we can use the let's say the conjugate. conjugating your conjugate, in which case, for instance, if you are asked to compute the limit when x tend to 9 of, for instance, x minus 9 over square root of x minus 3. So if we do direct substitution, you see that this will be equal to 9 minus 9 over square root of 9 minus 3. So this will be equal to 0 over 0, which is in the determinate form. So to deal with this, use conjugate. So we have to multiply the numerator and the denominator by the conjugate of our denominator. So our limit will be, limit when x tend to 9 of x minus 9, then we multiply by the conjugate of the denominator. The conjugate is the square root of x plus 3, then over square root of x minus 3 times square root of x plus 3. And you can see that this will be equal to x minus 9 and times square root of x plus 3 over, then denominator will be equal to, this is square root of x squared, which gives x minus 3 squared, then minus 9. Then x minus 9 and x minus 9 is simplified. Of course, here we have to have limit. This is equal to limit when x tend to 9. So this will be equal to limit when x approaches 9 of square root of x plus 3. And this will be equal to square root of 9 plus 3, which is equal to 3 plus 3 equal to 6. And let's take an example where we can use trigonometric identities. Of course, when we have trigonometric expression, that's when we can use trigonometric identities. I give you an example. Let's take this function, this limit, example number 3, using trigonometric identities. Example, I give you an example. This is example number 3. Then example, if we are computing limit when x tend to 0 of this function sine x over, let's say, sine of 2x. So you see that the direct substitution will be sine of 0 over sine of 2 times 0, which is equal to 0. So this will be equal to 0 over 0, which is a determinate form. So the identity, trigonometric identity that can serve us for this case, it's just replacing sine 2x by this one. 2 sine of 2x is equal to 2 sine of x plus times cosine of x. Yes, I think you know this identity. The identity that says that, let me write it here, that says that sine of a given function is equal to 2 times, so it goes away. It goes away. Let me use another color then so that it can stay and you can see it clearly. So I'm using this sine of, let me say, a. This is equal to 2 sine of a over 2 times cosine of a over 2. So this is the identity that is saving me now. Then I have this sine of 2x to be equal to sine 2 times the sine of x times the cosine of x. And then our limit will become, what? We will have limit when x approaches 0 of sine x, and then we replace sine of 2x by 2 times the sine of x times cosine of x. So this will be equal to, I simplify sine x and sine x, then I remain with limit when x approaches 0 of 1 over 2 times cosine of x. And the direct substitution then will give us 1 over 2 times cosine of 0. And cosine of 0 is equal to 1, then equal 1 over 2. So you see, things are becoming very, very easy. So you see, all right. Must know number 5. The fifth thing that you need to know is the laws of limit laws. The first law is that, let me write them down. The first law is that limit of the sum of functions, limit when x tend to a of a sum of two functions, f of x plus or minus, of course, gx. This is equal to limit of the sum of limits. So limit when x tend to a of f of x and plus limit when x tend to a of gx. This is the first law. And the second law, it's a limit of a function times a constant. Limit when x tend to a of a given constant, c is a constant, then times the f of x. This is equal to that constant c times limit when x tend to a of your function f of x. You have to know this. And third, it's the limit of the product and the limit of quotient, of course. So if you have limit, to calculate limit when x tend to a of a product of two functions, f of x and times gx. So this is equal to the product of limits. So this is the limit when x tend to a of f of x times limit when x tend to a of gx. And this is can apply also to quotient. If we have f of x over gx limit when x tend to a, so this is can be the same as the limit when x tend to a of f of x over limit when x tend to a of gx. Yes. Must know number 6. The sixth thing that you need to know is how to calculate the limit of a function at infinity. Evaluating the behavior of a function at infinity when the values of x tend to either minus infinity or plus infinity. So what you need to know first, let me say this. We need to know that a line, let me write it down, a line y equal b is the horizontal asymptote, yes, asymptote. There is am I writing it correctly? Asymptote. Let me write it well anyway. Asymptote, yes, asymptote is the asymptote of a function let me write it this way, a function f of x if limit when x tend to plus infinity of your function f of x exists is equal to exist and is equal to b, or limit when x tend to minus infinity of f of x exists and is equal to b. So that's why it is very important to know the behavior of a function when the value of x goes approaches either plus infinity or minus infinity. So I must know. So how do we compute the limit at when the values of x goes to infinity? Let's see an example here. An example, let's say we are asked to compute limit when x tend to let's say plus infinity of this function, 5x squared plus 8x minus 3, then over 3x squared and plus 2. If you do direct substitution, you will find infinity over infinity. But there is a way to deal with this. What you have to do, you have to see the highest degree of your polynomials on the numerator and the denominator, because we have polynomials of the same degree. So then in our case the highest degree is 2, and now we can multiply by 1 over x squared by numerator, both numerator and denominator. If we multiply by 1 over x squared, both numerator and denominator of our function, we will have something that looks like this. Limit when x tends to infinity of 5 times x squared over x squared and plus 8 times x over x squared minus 3 over x squared, and then over 3 times x squared over x squared and plus 2 over x squared. So you can see that this is the same as limit when x tends to infinity of this x squared, and this one are going to be simplified. Then we remain with 5, and then plus here x and the square are simplified, then plus 8 over x and minus 3 over x squared, and then over 3, this we simplify this and this, then 3 plus 2 over x squared. Now you can see that this will be 0 and this will be 0 and this will be 0, and we will remain with 5 over 3. So when the numerator and the denominator has the same degree, what you do, you only take the quotient of coefficients of the terms of highest degree of your variables. So for this case we have this 5 over 3. But what if the numerator has the degree of polynomial on numerator has a small degree compared to the denominator? So in that case you will have 0. The limit will be equal to 0. And if the numerator has the highest degree compared to the denominator, so then in that case you will have infinity. So yeah, that's the thing that you have to know. So when you have the limit at infinity, and if the limit exists, then the most thing that you have to know is that you will have horizontal asymptote. For instance, in this case we will have a horizontal asymptote. We have horizontal asymptote of equation y equal to 5 over 3 when we go to infinity, when x equals to infinity. So okay, yeah, that's another important thing that you have to know with limits. All right, must know number 7. It's the L'Hopital's rule. The L'Hopital's rule is applied when we have these two indeterminate forms, when we have a limit to be equal to 0 over 0, or when we have infinity over infinity. So the L'Hopital's rule saves our time. And how does it work? The L'Hopital's rule says that the limit when x tend to a given value, let me say a or c, let me say a, of a function f of x over gx, this is the same as limit when x tend to a of the derivative of the quotient of derivatives of a function. So of f of x derivative over gx derivative. So this rule is also much used. So it's a must know when you are dealing with limits. Let's see one example where we can use the hospital rule. For instance, if we are asked to compute this limit when x tend to 2 of this function, x squared minus 7x and plus 10 over x minus 2. So you can see that if we substitute by 2, this is it this will be equal to 2 squared minus 4 minus 7 and times 2 and plus 10 like this. So and over then x minus 2. So then over 2 minus 2. You can see that this is 4 plus 10. This is 14 minus 7 times 14. Then 0 over 0. We have this in the determinate form. So to apply the hospital rule, we must calculate the derivative of numerator and derivative of denominator. And then this limit will become limit when x tend to 2. The derivative on numerator will be 2x then minus 7 over the derivative of denominator is equal to 1. So this will be equal to limit when x tend to 2 of 2x minus 7, and this is equal to 2 times 2 and minus 7, and this will be equal to minus 3. So see, the hospital rule is very important and it's something that you should know about limits. Must know number 8, other indeterminate forms. There are other indeterminate forms, and those forms that I want you to know is these forms. The form 0 times infinity and the form infinity minus not minus 8. It's minus infinity. Infinity minus infinity. These indeterminate forms should be known too. And to deal with this infinity, you have to use some tricks and try to transform these forms into these two forms. You try to transform these forms into 0 over 0 form and the infinity over infinity forms, so that you can apply the hospital rule to solve your to calculate your limit. I will give you an example. Let's say you are asked to compute the limit when x tend to 0 to 0 plus at the right hand side of 0 of this function x ln x. I say 0 plus because ln x is defined from 0 plus it, because in 0 it's not defined, so it's not continuous in 0. Then that's why I'm calculating and the 0 plus. So this will be, if we do direct substitution, this will be equal to 0 times minus infinity, which is in the determinate form. So to deal with this, we have to try to transform this, let's say, at least into infinity over infinity form. But how? This can be like a limit when x tend to 0 positive of, let's say, ln of x over 1 over x. So this 1 over x, which is a denominator, is the same as multiplying x here. So I don't change anything. And you can see that this is equal to minus infinity over infinity. And with this, we can use the hospital rule to solve this one. And see, if we use the hospital rule to this one, then what are we going to get? We will get limit when x tend to 0 positive of our function will be equal to ln of x derivative over my 1 over x derivative, like this. So this is equal to limit when x tend to 0 positive, derivative of ln of x is 1 over x, and the derivative of 1 over x is minus 1 over x squared. And you can see that we can simplify, and if we simplify, we will get this to be equal to limit when x tend to 0 positive of 1 over minus 1 over x, and this is equal to minus this is limit when x tend to 0 positive of minus x, and this is equal to 0. So you see, yeah, when you have those two forms, just try to transform this into either this 0 over 0 or infinity over infinity. And depending on the case, this case here, you can also use conjugate. And using the conjugate, then you will get to transform it into this form. So you see, this is also a must know. Okay, must know number 9. It's the theorem of squeeze theorem. And this theorem, what does it tell us? It tells us if the theorem says that if we have f of x, a function f of x, which is less than or equal to gx, another function gx, and this function also is also less than or equal to another function hx, when x is near a given point a, except at that point a, and if the limit of the function f of x when x approaches a is equal to limit of hx when x approaching a is equal to a, then it is indicator that the limit of gx when x approaches a is as well equal to a. Yeah, and this squeeze theorem is also very important when we are calculating limits. So let's see how an example of where we can use this theorem. Let's say we are asked to compute the limit when x tend to 0 of this function, x squared times sine of 1 over x. Yeah. How can we apply this squeeze theorem? What we know is that sine of 1 over x is always less than or equal to 1, and is always greater than or equal to minus 1. This is due to the function, the behavior of our function sine x. It is always bounded by minus 1 and 1. So you see, our function here that we have, it's sine x times x squared. So this means that if we multiply here x squared to sine x or sine 1 over x, this means that this will be equal to less than or equal to x squared, because it's x squared times 1, and greater than or equal to minus 1 times x squared. So right, and then this limit, this you can see that limit when x tend to 0 of course it's 0 when limit when x tend to 0 of this function minus x squared will be less than or equal to limit when x x tend to 0 of our function x squared times the sine of 1 over x. This is x, 1 over x, and less than or equal to limit when x tend to 0 of x squared. So you see that this one limit when x tend to 0 of x squared, this will be equal to 0, right? Yes. And this one also, this one will be equal to 0. So you see the limit here, if we take a function, our function f of x to b minus x squared. Let me take this one a little bit up. Yes, if we try to apply our theorem, let's consider f of x to be equal to minus x squared, and then gx will be equal to x squared times the sine of 1 over x, and then hx will be equal to x squared. So, and we have already proven that limit when x tend to 0 of f of x is equal to limit when x tend to 0 of hx, and both are equal to 0. So then we deduce that this is an indication that limit when x tend to 0 of our function gx, which is the limit when x tend to 0 of our function x squared sine of 1 over x, this will be also equal to 0. So you see, the squeeze theorem is also a very important theorem to know because it's useful to calculate limits. So you see, must know number 10 is the epsilon delta definition of limit.